make sure we get through the intro. All right, homework 0 scores and homework 1 peer reviews are out. Has anyone not gotten a homework 1 peer review? All right, good. Please do those soon so that we can also start grading. Homework 2 is out, due November 2nd. Please look at it soon, especially since, skipping to the bottom, we'll do a review on Wednesday, and I'll happily answer most questions, particularly anything about homework 2 or past material or whatever. So look at homework 2 soon. Post questions on Piazza so I can prepare the answer, or bring your questions on Wednesday. But make sure to do this. If you're having trouble with Python in homework 2, so a couple things. One, if you ran the Python test thing, which I know you all did because you're all good students, if you have that set up, you may need to take some elements out of what we got working for your machine and put them into the homework. That's not too difficult. But if not, then there just may be other adjustments. But let us know soon. If you can run every one of the homework 2 problems, you should be able to run the driver, whatever Python file is in there, and it should work. And it should use Python. It's just a lot of it's not optimized. So if it doesn't work, we want to find that soon, because you'll be, otherwise you're just doing sort of guesswork programming because you can't actually run it. So do that soon, okay? And then contact us as soon as possible if it doesn't work. If you did run the Python test, installation test, and it worked, then we know that we can make it work on your machine, and we may just have to go back and pull some things in. Yes? Are you supposed to copy the files in util to every folder? No, they should all import. They should all put them on the path. Every one of the driver programs should add util to the path and then import. So you shouldn't need to do anything. It should use util and import the things it needs as it goes. Okay, I mean, it's not in the perfect, I didn't make it a full Python module and all the things I was supposed to do, but it should work. Okay. All right, today I want to give a bit of an introduction to the architecture of GPUs because it's relevant to how we're going to program them. It's important to understand how they behave differently to use them efficiently. Most of my slides are actually stolen from someone who's given a lecture like this at SIGGRAPH a bunch of times. SIGGRAPH is the big graphics conference. It's where GPU computing really started. People, in fact, the GPU as compute started with people saying, oh, look, I can do certain programs with graphics hardware. Graphics hardware is there to draw triangles and figure out lighting equations and things like this. And people were like, oh, I can take my problem, like finding shadows or depth matching or things like this, and I can turn that into a triangle rendering problem. And then I can render it as triangles and read back the answer, and it's very fast. And then the graphics card companies were like, well, why don't we make that a lot easier? Partly because, it wasn't just that they wanted to cater to these people, but they wanted to make the graphics card more powerful. So we want to talk about how that was done and what the sort of choices are. So here's we've seen this drawing before, single core CPU. We've got a big cache, big L2, big L3. We've got the fetch decode logic. That basically reads the instruction stream and figures out what the hardware needs to do. So as the program comes in, as it goes through the program, figures out what needs to happen within the all the compute's in the yellow. All the actual things you care about are right there, all your programs. It's all in the ALU. So fetch decode looks at the instructions, figure out what sort of wires to turn on and off to make the ALU do its work. We have execution context. That's basically the registers that you have. If you've got a couple of hardware threads, you have 2 contexts that it can switch between very quickly or interleave instructions from. So this is all your registers and whatever you've stored, your temporary program, your local program state. You have a big cache to hide latency, and then a bunch of other things actually to hide latency as well. You've got out-of-order control, so it can look at your program. It can look at the instructions coming and say, oh, I can do this thing where I have the data available before this other thing that's technically before it in the program, and it's still valid. This happens all the time. You write a program and it's got multiple sort of directions it can go locally, and within the hardware, it'll do different instructions first. You've got a branch predictor because since memory reads are so slow, it wants to look ahead and say, oh, I'm about to jump to this other location, or I'm about to read this other location. I will preload into the cache that instruction that's far away. I'm about to do a function call. I say, okay, well, I know I'm going to do that function call in 10 instructions. I'll preload the code I'll basically get the cache ready for that, so that when I do jump to that location, it's already there and I don't have to wait. And so you get these basically branch predictor is what is your program going to do, and memory prefetcher is what data is it going to read. And there's a lot of logic in there. It's, a significant portion of the chip is trying to predict what your program will do in the future so that it can get the data ready because memory is so far away, right? It's all latency hiding. All of this over here is just to deal with the fact that memory is far away. So we put things in the cache and we try to predict what we're going to get before we need it. Right, so this is all about serial programs. I mean, not so much that we might have multiple execution contexts. That's gonna help several different serial programs. But this is all about, I've got one stream of instructions, how do I make that set of instructions run very fast? How have we seen to speed this up? What's the most common idea since 2004? Well, that was more the SIMD thing. More ALUs is true, but wrapped in multiple cores, right? Want to make my compute faster? I have a bunch of transistors. I can't just we hit this limit where we couldn't make the clock speed go up, and the cores were getting too big, at around 2004-ish. So now we'll just stick more cores in there. Very easy to get more performance packed in there. We still leave a big shared cache, but we tend to push the L2, still a fairly large cache, into the individual cores, and we get however many cores we can pack in there, and that just keeps going up. Right? The other idea that we've done also is SIMD, which we just finished talking about, and which we'll experiment with in homework 2 some, where, all right, we've got a lot of compute that is on similar data, and we're gonna do exactly the same thing to it. So we'll add a bunch of ALUs. This is very simple logic. It's easy to duplicate. It's simpler than a core, so we can pack more, just these smaller pieces in. We still have only one stream of instructions coming through the fetch decode, right? SIMD is one stream of instructions, but multiple data. So we don't have to duplicate that logic so much, and we can reuse a lot of what we saw in the other picture. But we can get all this other computation going on, and then we have little contexts for each ALU, where these are sort of the SIMD registers, or one slice of the SIMD register. So this would be the SIMD register 0, or the values for SIMD registers in the first position, second position, and then they talk to those ALUs. All right, that's clear, what I'm talking about there, how these contexts are split across the ALUs. It's just that if you have 8-way SIMD, then you have, those contexts are split into 8 pieces and talk to the multiple ALUs. And the other answer for speeding this up is just add a lot of cache, right? We've got this very narrow, comparatively, pipeline, 25 gigabytes a second or so for DDR3, which is around where a lot of it's sitting. 25 gigabytes a second is not slow, but it's not fast enough for a lot of compute we can do. And so because this is fairly narrow, and we'll see how it compares to GPUs, this is very narrow, we put a lot of cache here so that when we do need data or instructions, we don't have to go very far. We don't have to go all the way to memory to get it. All right, so we front load a lot of cache to hide latency, to make this seem to run faster. Basically, we need to, it also allows multiple threads to interleave because they are looking at different places in memory, but we have a large cache, so they're storing them in different places, okay? So these are sort of the main things we've done to speed up single core processors. So how does SIMD interact with the control logic in the cache? When I'm dealing with objects that are larger than one float, I'm talking about 8 floats or 16 floats, how is that going to interact with the cache? Thoughts? Speculations? So in general, is the data going to be scattered or fairly dense? Is it going to be coherent? Like if I'm doing graphics, if I'm doing sound processing, if I'm doing image processing, is my data all over the place? Or is it, if I'm going to use SIMD, I'm probably working on a problem that's fairly packed, right? And the control logic, as I said, is the same. So really, the SIMD doesn't change things too much here. And so what happens with GPUs is they say, okay, let's just get rid of this. It doesn't, we can do, like before we had fine computers, right? They were very fast. All of this was because things were slow, right? Memory was slow, single instruction is not very well organized, we're jumping all over the place. Throw this out. I'm just gonna dump it all into SIMD, right? This is what GPUs say. It's basically, I'm just going to take SIMD, and that is the horse I'm going to hook to my cart, and we're going to go. I'm not going to do anything else, all right? So when we look at, for example, a modern CPU, the Core i7, 4 cores, 8 SIMD ALUs per core. So you have 32 ALUs. Which is a reasonable number. It runs pretty fast. Has all that other logic in there as well. This is the NVIDIA GTX 480. 480 comes from these two numbers. You have 15 cores on this chip. 32 SIMDs on each core. And that's basically all. Does 1.3 teraflops. This is from years ago, too. This is GTX 40. I don't know. Someone can look on Wikipedia. It's been out for a while. It's still pretty fast, comparatively. This is almost all the logic on the chip. There's memory interface and stuff, but there's not a huge L3 cache. There's nothing else. We've thrown all that away. There's no out-of-order prediction. All we have are these workers. Basically, these cores, a bunch of them, and a huge amount of compute. Basically, raw compute there for the taking. How do we get at this compute? What does it look like? So we've got the fetch to code. We still need that. In each core, you have a couple of them, so it can do a couple of upstreams. But basically, the SIMD functional unit is control. They all do the same thing. They share the fetch decode logic and the ALU control across 16 units at a time. Okay. And that's split across two. So there are 32 ALUs per core. It has some local memory, the execution context, that's what we talked about before, the register, and we'll talk more about this, and it has some shared memory, and this can also be used for cache. It's basically to allow reasonably fast communication between cores. ALU stands for Arithmetic Logic Unit. It's where all the computation actually happens. That's the only place where the computation happens in the computer. All the rest of you look at a layout on a chip. I should have pulled in one of the physical layouts. ALU is about 10 to 20%, and all the rest is cache, branch prediction, memory interface, things like this. So all the actual compute, that's where things get added, multiplied, all the instructions that you actually execute. The rest of it's then, most of the rest of your program is pull something in, do something to it, and store it back. But that's just where a computation happens. So they're dumping most of their chip real estate, or a lot of their chip real estate, into compute. And then it's how do you make that available now that you don't have, how do you take advantage of that without these other helpers like cache and things like this? So if you're going to have a lot of compute, you're going to need a lot of bandwidth to keep it fed. So one of the main differences between the CPU and the GPU is that memory bandwidth. Right, we have 25 gigabytes a second or so, partly because the memory is off chip in a modern CPU, right? You've got the chip and you've got upgradable memory somewhere. But it's across a fairly narrow pipe. GPU always, always, always is going to have a very thick pipe. That is starting to change with more modern architectures, but GPUs still, because of they've got sort of a lead on CPUs, this memory bandwidth is always going to be high, but it's still actually kind of low compared to what we can do compute-wise. A lot of GPU algorithms, and we'll talk about this more in the future in a couple of lectures. A lot of GPU algorithms end up bandwidth bound, and that actually results in something like 3% efficiency. If you're just doing a vector multiply add, the fastest you can go, it's not compute bound, right? It's just multiply two values and store them back, like a dot product or something. Most of the limitation is going to be here, because you can do so much compute over there. All right. The other thing to notice, cache sizes. Shared L2 cache for all of the cores, all 15 cores, is only a few times larger than the L2 cache on a single core from our Core i7 or something like that. We have less than a megabyte of L2 cache, and that's as much as we get. We get a small local cache and some local memory storage, but we don't have a giant L3 to make things faster. So when we're doing GPU programming, we have to be very, very careful about how we read memory. right? We can't rely on the cache to take care of our mistakes for us. We'll talk about how that happens. I just want to make sure that you're aware of that limitation for future reference. Okay. Given that we don't have all these caches, we don't have out of order execution, branch prediction, things like this, the way that we hide latency in GPUs is more threads. All right, we're familiar with this concept so let me go back to this drawing. Right. In the Core i7 or modern architectures, we might have, and usually will have, 2 hardware threads. We talked about this, how there are basically every core is split into 2 virtual cores that can interleave their instructions very quickly because we have 2 sets of registers on the core itself, basically 2 execution contexts. And when one execution context can't do work, the other one jumps in and uses some of the processing power, or if they're using different parts of the chip. And that allows us to hide some of the latency too, right? There's some latency hiding there. That is really the only latency hiding for GPUs. And instead of just having 2 hardware threads, we can pack a lot. So back to this execution context memory. We have 128 kilobytes there to store whatever, generally just your processing state, right? If I'm doing a computation that involves 5 values and keeping those around, then I need 5 times however large those values are, so maybe 4 bytes. Or 8 bytes. I need 40 bytes of memory to store that computation. And if I need to do a context switch and let something else run, I have to put that somewhere, right? I might store those off and then start up the computation later when it's ready. So to do that, I need to put them somewhere, and this is the execution context. It's whatever we need to pause the computation where it's at, do something else, and then bring it back into activity. So we have 128 kilobytes. And and that's the register, we can store register, program state, whatever else. Each core can basically have as many threads as if hardware threads that can switch between very quickly as long as it can hold their contexts. Actually, it's limited to about 50, depending on the hardware, or more. But that's per core. So 50 active threads per core, 15 cores on this one. I forget what NVIDIA is up to now. Active at a time. So we're going to hide all our latency by just having tons of threads active at a time. We're going to need to launch very large problems and deal with them in small pieces so that our processing now, instead of having 4 workers working on some image processing task, we'll have 10,000 workers. Any number, you will have 480 or 500 of them active at any one time, and the rest will be queued up by the system, but we will have a lot of threads. And so this influences how we program. This is something else to think about for the future, and we'll talk more about this. If you have many small contexts, if your computation is simple, or you can simplify it in some way so that you don't keep around a lot of values and then combine them. Right? We can either think about, we do a computation, we get 30 values, and then we fan them back in and combine them. Right? At some point, I need to store those 30 values. I might need to. And so that's going to take some amount of context. If I have 300 values, it's going to look more like this, right? If I have a whole bunch of values to store, I'm going to take a big chunk of my context memory. I'm not going to get very many possible threads, right, if I'm doing a bunch of this. And so I won't have very good latency hiding. I'll only have 4 threads per core or something pitiful like that. And at that point, all my latency, since my only tool for latency hiding is more threads, I've thrown that away. I'm going to get somewhat poor performance. This is called poor occupancy in the GPU lingo. Basically, I don't have a lot of things going on at once because I can't store their state. We much more want it to look like this. So, yes?
Why did you say it would look like the last slide if you have 300 values?
So, I've got a bunch of computations I'm going to do. I'm going to split that into, I'm going to have a lot of threads running, hopefully hundreds. Each thread has some amount of memory it needs in order to be able to it needs to reserve some memory in case it needs to suspend, right? It might go to read something, it might need a value from memory, and that's a long way away. That's gonna be 20, 30 cycles away, right? While it's doing that, I want something else to happen, right? Let me just do a drawing of this. So I've got some thread going, right? And it's computing along. And then it reads some memory fetch, right? And it's not gonna be able to run again till, this comes back some amount of time later. So this is called a stall. Okay, so I've got one thread running here. And what I want is, okay, well, while this one waits, I'll start up another I'll let this thread run, right? And at some point, it's gonna make a memory read, and it's also gonna stall, right? Because you have to read memory. So I want another one, and another one. When this one stalls, it has some intermediate state. It's got its registers, it's got its program counter, things that are involved in the computation that's gonna go forward. It has to put those somewhere while it's not running. When it stalls, those have to be stuck somewhere for future reference. And that's that program, that context. So it takes a slice of the context memory somewhere, over here, and puts them there. And then when it's asked to run again, it brings them back. That's very fast. That's like, not quite as fast as registers, but close. Same thing here. When this one stalls, it takes another slice. And it pre-allocates these. It knows that the compiler knows, and the system running this knows at any time how large the context is, or potentially is. And so it doesn't load the threads in here if there's not space to store their context. So if my context is small, I can fit 40 or more. I can get close to, I think the maximum on this hardware was 48. That's as many threads as you could get. But if my context is small, I can get that. Right? If each one only needs a small slice, then I can pack however many fit here on here, and then whenever one stalls, there's another one ready. So I can handle a lot of stalls and still be doing compute. Now, if this one had a very large context, right, it's gonna take half my context memory, and that's extreme. Which means, if this is the same sort of task but running on a different piece of data, I can only fit 2. And so when this one stalls and then this one stalls, now I don't have that to run. And so I get a lot of just dead space while it waits for memory or something. So our only tool in GPUs to hide latency of the memory system or whatever else is to just pack more threads in there. So we only have one tool, so we want to make good use of it. To do that, we have to make sure that we're doing basically simple computations that don't involve a lot of 300 values being combined, something like this. We'll see more concrete examples of this with actual code later. But does that answer your question?
Yeah, by 300 values, I thought you meant like 300 algorithms. You meant like some kind
I mean like some sort of, we've got some, right. Like I load a whole bunch of values and then I combine them later and I'm trying to keep them all in, I have 300 variables in my program. This is not a good program probably, right? If I've got one function and I'm listing 300 variables, probably type something badly. So is that clear? What I mean by context and why this is important? Okay, it'll become more obvious why this is important later, but you'll see some actual occupancy calculations and understand. So really it sounds great, right? I mean, more or less. It's a little bit strange that we have to compute this way, but it sounds like a great model. Right, get a lot of compute. Don't do all this complicated branch prediction, things like this, cache and things like this, which we know from previous lectures and experience. It's easy to do the wrong thing with your cache, right, or somehow screw it up. It's easy to make the cache actually not useful. So what's the catch? You only get SIMD instructions. There's nothing else. They can only do SIMD instructions. Every ALU at every step does exactly the same thing, exactly. So all you don't have integers, you have vectors of 32 integers. You don't have a float, you have vectors of 32 floats. You don't have a binary test, you have 32 binary tests. So when you're running your program, you might have 8 ALUs or 32 or whatever. You're just doing something like this, okay? A simple computation. You have, when you say A in your program, you actually have 8 copies of A with possibly different values because you've loaded them from different places in memory. And so when you execute that line, everything executes that line. Okay? When I do this, the next step, everything does that step. My computer result, I get 8 32 results. Doesn't seem so bad, except what about branches? Right? What if I want to do something different for some values? This is where it starts to fall down a little bit. What happens when you have a program like this running on a GPU is it does that test. Is x greater than 0? And then it figures out which ALUs that's true for, and it turns off everything else in the next block. So when I execute this program, it looks like this from my execution profile. I'm coming along, everything's going well. I test and store a true or a false value. And then where it was true, I run that code. And nothing happens on this other part. And then once I get to the else clause, I toggle which ALUs are on and do this compute, and then I go on. But that means that, potentially, only 1/8 of my ALU is actually working. If I have a bunch of chained logic, then it's quite possible I can drop to 1/8 peak performance. And at that point, I'm going quite slow, because actually GPU clocks are slower than CPU clocks by a factor of 2 or so. So when I'm doing complicated logic like this is called divergence. They also talk about coherent programming. Coherent also means memory coherence, which is also important for GPUs, but also just coherent program or instruction stream, where you find ways not to do this. Because if you do this, some of your compute is doing work, and some of it's just idling, basically. Why does the GPU work that way? Because, let me find a cat. There we go. The reason it works that way is because we're sharing this fetch decode. That fetch decode is the program counter. It fetches the instruction. It looks at what it is and decides how to make the ALU execute that instruction. So if it's a multiply of 2 registers, it says to the ALU, take these 2 registers, multiply them, and store the result in this other register. But we're sharing that for all the ALUs. We don't want to duplicate that logic. It's expensive logic. And if it got totally divergent, then you would lose a bunch of, basically if you didn't share that logic, then what if there's a function call in what part of it? Some of the ALUs are going to be off doing something else entirely. And then we're back in multi-core land, sort of. Right? You could have completely divergent programs. So what happens is they all have to be at the same program counter, just some of them aren't active. Okay. Anyway, so after we get through this if-else clause, then we get back to peak performance where everything is hopefully doing useful work. But this is something else to think about. You can't do just arbitrary conditional programming like you would in a single string. You wouldn't, in a multi-thread environment, you wouldn't worry about this, right? You would just, some branches would go and do something, or some threads would go and do something, other threads would go to another function, and you wouldn't be too concerned about the complexity of your program across threads, right? They're independent. They just go and do something. It's not the case here. All your threads do exactly the same thing at the same time. They do it very fast, but with limitations. So instead of caches, we don't have a large cache. So instead of using the caches, we hide latency with many more threads, many more, potentially thousands, and very high memory bandwidth. Like I said, so the typical CPU, 25 gigabytes a second. GPU 177 gigabytes a second and higher. I forget what it is now. It gets insane. It's approaching, I believe, terabytes a second now for some of the high-end GPUs. The other thing to notice, we don't have as much memory by default, usually, because it needs to be faster, needs to respond very quickly to the GPU request. So this is like DDR5, and so it's more expensive and so harder. You just don't get as much. But you can read it a lot faster, to the point that, well, yeah. No. All right, well, that went faster than I intended, so I'm sure I was confusing. So in summary, very fast, wow. Many, many arithmetic logic units. You're gonna be programming a whole bunch of very lockstep sort of objects with the same program. Many threads per core. That's where we get our efficiency and latency hiding entirely, just multiple executions, and then swapping between them when one of them is stalled. Very high memory bandwidth. This will become sort of, for GPU programs, memory bandwidth becomes the killer feature, both in terms of what you can do. Because you've got much higher memory bandwidth, you can do a lot of much cooler things, but also because your memory, you can quickly, because you have so much compute behind that memory bandwidth, you can fail to use it efficiently, the compute. You can't keep it fed if you're not careful, even with this. Right, so huge compute, huge memory bandwidth compared to a CPU, but keeping them working together is tricky. Because the trickiness, every instruction is a SIMD instruction. And usually 32 wide is sort of the default for NVIDIA hardware. Again, memory bandwidth has to be managed for peak performance. It's not just the bandwidth, it also has very constrained ability to read scattered values and things like this, which again, we'll talk about. All right. Questions? Wow. I tried to put in extra slides to take more time.
Are there Python packages that interact with GPUs, or do we have to like go into C now?
You're gonna have to go a little bit into C. So there are Python packages that can do some things, and we'll try to take advantage of those as much as possible. But in general, we're gonna end up writing, for OpenCL, you write something that looks a lot like C. There are some higher level wrappers for that. So we're actually gonna use OpenCL, partly because you don't need a GPU to use it. OpenCL is high level, sort of, it's not high level. It's higher level than CUDA or C. It looks a lot like C, and in fact is generally valid C. But you can write a program and say, run this on whatever I have available, and it'll choose the CPU, the GPU. If you don't have a good GPU, it'll just run on the CPU. It doesn't run fast necessarily, or as fast as it would. But it can take advantage of CUDA and a lot of the high performance things. It's also a really good introduction to building CUDA programs for people who are going to do really intensive GPU programming. So especially if you're thinking about a final project involving GPU programming, which since you don't know what that involves yet, may or may not be the case, OpenCL is a good bridge to that, and it can actually get you most of the way in terms of performance.
What's the workflow look like? Are we running some of the programming on CPU and then some applications with GPU and the other side?
Okay, so how does this work in terms of programming, in terms of the CPU, GPU? So the CPU will load down an image or a data set, basically a block of information, and then a kernel, which is basically a small program. And then it will say, launch this kernel, launch 10,000 threads of this kernel. If I have 10,000 rows in an image, I want to process them independently. It'll say, launch 10,000 processes on the GPU, and each one just gets an index and a memory pointer. The index is a thread. So it's basically its thread ID, and it uses that to start, basically to split up the work. It's sort of static scheduling. So each thread will say, oh, well, my index is 500. I will go and find row 500, and I will just start processing along. The GPU does all the rest in terms of scheduling. You've got 10,000 threads. Not all of those are going to fit necessarily at the same time. It'll take that big block of memory that you loaded down, produce another result of some sort, which you will read back. So that launching, sending things to the GPU and reading back is slow. It's like Spark, it's like the shuffle step. You want to keep everything on the GPU as long as possible and read back as little as possible. And then there's a whole bunch of things in the middle as well. So.
Yeah, so is it the case that there are many ALUs per core, like 8 per core, or is it shared ALU?
32, 16 actually that run double speed. I mean, it depends on the hardware architecture. In this one, there were actually 16 ALUs per core. They run twice as fast as the regular clock, so they look like 32 ALUs. But
Is that how it supports the many threads per core by having a lot of ALUs?
Two ways. One, a big context storage. So you can store as many, so I'm using threads, and so it's sort of a mix of threads and SIMD. If you have multiple kernel executions going at the same time, think of that as the thread. And you can pack as many on there as you can store their context in the context storage. You also are then doing everything SIMD-wise. So you have maybe, you could have 20 or 30 threads running on a core, sort of like hardware threads, switching between these whenever one is not able to run. And then within that, there's a little program, but each line is a SIMD instruction. It has, every variable, you have 32 copies of it somewhere, and it executes a SIMD instruction per step across those 16 ALUs.
So I just got this. So the transfer between GPU and CPU is slow, but GPU and memory is very fast.
GPU and GPU memory is very high bandwidth and reasonably fast. So GPU has its own memory. That memory is separate. Sorry, that wasn't clear from the drawing. The GPU has its own memory, and it's small compared to it's gigabytes, small gigabytes, and the computer memory is going to be multiple gigabytes. So you take an image from CPU memory, push it to GPU memory, and that takes a while. And then on the GPU, you say, do something with that, produce a new result, and then I read that back to memory. No. The latest NVIDIA can actually, you can reference CPU memory, and it doesn't even do that. You don't have to do the transfer yourself. NVIDIA has this new interconnect that it's pushing, which makes the CPUs and the GPUs and memory all talk on the same bus, that same super high bandwidth bus that they use for their own memory. And NVIDIA's pushing one, Intel's pushing a different one. They will fight. What if your problem can't fit into GPU memory? Get a bigger GPU or break it up into small pieces.
And then like push.
Yeah, then you push things like this. You can interleave data transfer and computation, usually. So you'll launch the compute and then load down the next piece while it's running. Right, so what can you do on GPUs? What problems are suitable? A surprisingly large number of things. So physics simulation, even like free body physics simulation. I should have pulled up the video. There's this PhysX. If you search YouTube for PHYSX NVIDIA, this is their physics simulation system, which you can just, they have things bouncing around like crazy, and you can spray water and stuff. And it doesn't seem like a really lockstep sort of computation you'd expect to be good on a GPU, but it does quite well. People have done all kinds of things on it. You can bend it to your will. You just have to think very carefully about the problem. A lot of it is image processing or graphics. Things like this are very easy, but sound processing, deep learning is really so if you're familiar with deep learning, basically these very complicated neural networks, they map really well into GPUs. Matrix, anything you can turn to a matrix multiply. So do you come up against memory constraints? You do, but deep learning deep learning doesn't have a lot of memory. Physics simulation doesn't have a lot of memory. It has a few small values per object. Yes, so really large memory problems. Yeah, text processing, not so good on a GPU, depending on the size of that data. graph processing, you can do it. It's not, GPUs like very regular memory access patterns, which graph processing generally doesn't have. We'll talk more about what works and what doesn't. I'll bring in some examples. One second.
Sorry, two quick things. So is there any like libraries or stuff that you've been using that or like for other languages that use that or like?
Are there libraries we've been using that take advantage of SIMD already? Yes, NumPy. NumPy, in fact, will take advantage of multiple threads by default. If you do some large matrix multiply and then look at, if you're on HTOP, if you installed this, it shows you all the cores and it'll peg them all because it's dropping down into Fortran multi-threaded and SIMD libraries automatically. So yes, and the compiler can sometimes vectorize instructions as well, can realize that your computation can be mapped to SIMD and will do it automatically sometimes. And the other.
And like, will using some Python be faster than just writing in pure C?
Will writing SIMD in Python be faster than writing in pure C? So if you write something in pure C, you're almost always going to be faster than the Python. It's just whether it's going to be faster than you could have written it in Python anyway. The other thing is that when you use something like NumPy, OpenCL, if you're using any of these OpenCV library for vision, if you're using SciPy for computation, things like this, they go into C. NumPy is almost entirely C code. It's just got wrappers around it. So an array, when you do a multiply, it drops down into LAS, the linear algebra library. All these are written in C or Fortran. A lot of SciPy is in Fortran for speed and historical reasons. So when you write something new in Python, it's going to be slow, and then you might translate it into Python. And then if you need that last bit, you might translate all the way to C and start organizing it that way. But like we said, if you stay in interpreted Python, you're never going to be fast. But almost always when we do anything of interest, you drop into something faster right away.
Can you do complex operations if your context is small enough, or are you sort of restricted to like multiply and add through the ALUs and stuff? Like, can you do a matrix inversion in each context?
Can you do a matrix inversion in each context, or can you do complex operations if your context is small? You can do fairly complex things within that small 32-word or 32-element SIMD vector. And you have the ability to communicate between ALU elements with a few limited instructions. So you can do very complex things there, and you're saying maybe not go to memory, for example, if you've got, you probably don't have a context. I don't know if the context will hold like a square 32 by 32 matrix, but it would be interesting to see. You can, and if you don't go to memory, it will always be running, and it'll be quite fast. So if you can phrase your computation in a very small, very computationally dense compared to memory reads, you'll get very good performance. But you're going to be limited to 32, and possibly it's going to be hard to get 32 of those if you're talking about a matrix. All right, other questions?
Yeah, a little graphics computations. I always thought matrix computation, but that's not really what GPU is for.
So the question is, graphics computation seems to be a lot of matrix computation, right? But that's not really what GPUs are for. They can do matrix computation. It's just most graphics computation is not big matrices. It's usually 3 by 3, 4 by 4, moving points around. So it's very small matrix computations, and so these fit very well into the graphics hardware. Much more of the computation actually goes into things like lighting calculations and texturing and bump mapping and making things look real on a very local place. And the reason GPUs look like this is because you're doing this, you've got a large area of the screen you're going to cover with something. Every pixel has to be computed independently, and so that's basically what it does. It takes some complex computation and breaks it down by pixel, and then each of those runs in parallel. Okay. More questions? All right, Wednesday review. Look at homework 2. Ask questions. It'll be easier if you ask them earlier. If you ask them later, it'll be harder. Which do you prefer? Friday, there'll be the intro to Odyssey, making sure that all your accounts work and things like this. We'll also have some OpenCL examples for that running on Odyssey for you to test to make sure your environment is set up correctly. So you can do some in-class examples. We'll send that link out beforehand. So if you didn't get an Odyssey account link, do let us know. Okay, thank you.